In trigonometry, it's often helpful to take a look at some triangles that we consider special triangles from our geometry experience. One is an equilateral triangle. In Euclidean geometry, this means that all of the angles are equal, all of the sides are equal. So if I were to drop a perpendicular between any two equal sides, I have a geometry theorem that says we actually bisect the angle as well as the base of the triangle. So basically the relationship with a 30, 60, 90 right triangle is that whatever the hypotenuse is, the side that is adjacent 60 degrees is 1/2 of the hypotenuse. And I would say it's easy to find the third side with the Pythagorean theorem. So if you think along those lines, and we can actually convince ourselves that it really doesn't matter what the value A is as long as it's positive and makes sense in context with a triangle, that if we were to say pick a special triangle with these properties, maybe I say, okay, I'm going to pick a value of A equals 2, then 1/2 of A is the value 1, and the Pythagorean theorem would lead me to conclude that the missing side here is the square root of 3. Using our trig definitions, and you could go through, you can and you should go through all 6 yourselves. The sine of 30 degrees, for example, would be the opposite side divided by the hypotenuse. The cosine of 30 degrees would be the side adjacent 30 divided by the hypotenuse. Likewise, I'll put this up here, the sine of 60 degrees would be the side opposite 60 divided by the hypotenuse, and the cosine of 60 degrees would be the side adjacent 60 divided by the hypotenuse. And you might ask, does this work regardless of the value A? And the answer is yes. So if I were you, I would pick another value of A, maybe make A equal 1. Then this side here that I'm circling would be 1/2, and so forth. And take a look and see what kind of triangle you get, and redo the values and convince yourselves that these values are well defined. Now, if I were you, I would make an entire list and do all of the rest of these guys. Okay? All right, we're going to also take a look at the 45, 45, 90 right triangle. The 45, 45, 90 right triangle is a right isosceles triangle. So you have two equal sides, and when you apply this Pythagorean theorem to the situation, that would lead you to the conclusion that the hypotenuse is the square root of 2 times the original side length but me personally, I think what is important here is for you to remember a triangle to get your trig ratios. So I would like to propose that we remember the triangle with two equal sides, which are just 1 unit in length, and then the hypotenuse is simply the square root of 2. Okay, if I follow my nose here, I would say the cosine of 45 degrees, pick one of the angles to focus on because they're both the same, is the side adjacent 45 divided by the hypotenuse, and the sine of 45 degrees is the side opposite 45 degrees divided by the hypotenuse. And if you were to choose to rationalize the denominator, if you wanted to, you don't have to, you could see that 1 over root 2 is the same as root 2 over 2. Now, Again, I picked these two legs. So if you pick two other legs and produce the hypotenuse, then you should be able to follow through with the definitions and conclude the same result that I have. Now, if I were you, I would go through and write down the, tangent, cotangent, secant, cosecant, all 6 values for both of the special triangles.